Good. Welcome everybody. I like to say good night, but good night is a welcome as well as it's an end. It is just about 10 o'clock. It's 21:59. 21 hours and 59 minutes into the day of Tuesday, July 8th. 2014, and we're gonna begin our live broadcast now. Just about a minute early. A little bit of a programming note. We're going to be going from tonight. We'll be finishing up early. We're going to be, instead of going till Friday, we're going to finish on Thursday night. Thursday night will be our last broadcast for the week. And then we will probably come back on Monday, Tuesday, Wednesday. That's our when we will come back. It depends. Wednesday night will depend on when I am going up to my research expedition. Depending on the time I leave on Thursday, that's going to determine whether or not there's going to be a Wednesday broadcast. But we will be starting back on a regular basis when I get back around August 10th and 11th. That's when we will start again, and we will go from Monday to Friday. And we will have our talk live, and it'll be 3 hours. So the first hour is on YouTube, the second hour is going to be on YouNow, and the third hour is going to be on Twitcasting. And I think I'll post that here. Oh, wrong one. Sorry about that. That's our one. That's the Interesting. It doesn't seem to be in the clipboard. So, anyways, yeah, we're gonna be doing just about 3 hours live. First, we're gonna be on here. We're gonna then move over to YouNow, and then from here from YouNow to Twitcasting. You can sort of follow along. I had it on here once before, but I can't remember exactly where things are to sort of. All right. But anyways, on to our tonight's topic, and we'll certainly get a slow start to this. Let's see. So now let's where we're going to go from here. The reason why I brought up the topic is atheism dead, and it's not actually. You would think that this is a theological question, or this is a religious question, a question of religion, but it's not. And it's actually a question of science, because you have to consider where atheism came from. Atheism is a claim based on science, particularly what is now called classical science. And it is simply assumed that atheism follows into modern science, into current science. But the reason why I say current science as opposed to modern science is modern science and classical science actually are past tense. It's modern science is not necessarily mean current science, and I'll give you the reasonings for this. Science and philosophy are heavily intertwined. If you do your research and you look into the history of how science emerges, you'll find that history and philosophy are rather or significantly intertwined. That they are significantly linked. And when you look at the periods of philosophy, you'll find that the periods of philosophy actually match up very well with periods in science, and specifically the lead science, what I call the pinnacle of all sciences, that's particularly physics. Then everything else after that, all the other sciences after that follow. If physics always leads, because almost every subject that you could think of in science actually has some degree of physics in it. So use these classifications, and then you can get a pretty good idea of where we stand. So where are we in terms of our science, in terms of our timeline? Well, the thing is that we know from our look into history and philosophy that we are in the postmodern phase of philosophy. As a matter of fact, the postmodern phase of philosophy it began in 1945 with the explosion of the atomic bomb. Then, before then, from basically late 1800s to about 1945, you had the modern period of science, and before the late 1800s, that's what you would call the classical period of science. And I'm talking the classical period of science, that would be Newton. That would be a lot of the science that came out of England, France, and to a certain extent Germany, and these were would be the early pioneers, sort of on the tip of the voyages of discovery. So it basically covers the 1800s. The 1800s were really the what you call the classical period. The early part of the 1900s was the modern period, and then 1945 with the atomic bomb, you really began the postmodern period of science. And what had happened in this, we'll go from the physics perspective of this. The physics and science perspective in the 1800s and into the early 1900s was that science was pretty well deterministic, that the universe was, that you could understand the universe in mathematical laws. And this is exactly how the scientists approached this. You created a number of laws. You tested these laws out to see that nature fit within it. In other words, you test. This is the whole purpose of experimentation. You have hypothesis, method, observation, and conclusion. And the reason why you have this is you're going to take your theory, you're going to test this to make sure that that your theory, that experimentation meets your theory. You seek to prove your theory, and then if you do succeed in proving your theory is correct. That's the scientific method. And it was believed in this manner that this manner was sort of because you sat down and you did your theoretical work first, you did your mathematical work first, you did your mathematical model first. Then after you did your mathematical model, then you sat down and worked out what experiments you'd be doing to demonstrate this. This is the classical method that emerged, although it was not specifically the method used by people like Newton. Or even Galileo. Galileo did a lot of experimentation first and measurement prior to writing down his equation. In other words, while the classical method puts theoretical work first, the period prior to the classical method, and Einstein was around in the period prior to the classical method. The classical method was pretty much set around experimentation. It wasn't actually theoretical. It was after the work done by Sir Isaac Newton and before him Galileo that it was during that period of Galileo and Newton that's where you had a lot of experimentation. And then afterwards, that period afterwards, sort of sat on top of this stuff. And that was the 1800s when you had sort of the application and the use of the work done by both Galileo and Newton, that's when you sort of have the attitude in science that sort of forms the classical period. That this was known as the rational period, where everything had to have a rational explanation. There was no hocus pocus and all the other words like higgledy-piggledy sort of came about from the English vocabulary as they sat down and tried to describe nonsense. And the thing is they viewed anything that was not explainable as hysteria, hallucinations of the mind, illusions, trickery, and then they came up with the term higgledy-piggledy and so on and so forth. And so that was sort of, if you will, the beginning of the deterministic universe. A universe that was set in its rules, that had law and order, and was very well structured. And that's sort of continued. That's the way it was for most of the 1800s until some scientist came along named Planck. And Planck started fiddling around and asking questions like most bad people do. Started asking questions that he shouldn't be asking, and doing experiments that he shouldn't be doing. Normally, you're supposed to do an experiment to test, see, and prove your theory correct, and that's about it. You're not supposed to experiment and really explore around outside the boundaries of your experiment. You know, you're not supposed to go in. Let's see what's going to happen now. You know, but that's exactly what he did. He sat down and began. He looked at wavelengths, and he looked at particularly heat absorption. And Planck's best-known work is actually for the furthering and the advancement of black body absorption. So if you're interested in global warming, the first place you have to go to understand global warming is Planck, and into experiments on black body radiation. That's exactly what you have to look at if you're looking into the understanding. If you want to understand and look for global warming, you need Planck's black body radiation. The work in this particular area is what needs to be looked at, and then you go from there on out. And what he did is he started taking orbs and objects and heating them. The theory stated that if you kept heating an object, that the object would get hotter and hotter and hotter and hotter. In other words, it would continue to get hot. You wouldn't get to a point and then start dropping off again. In other words, the heat, in terms of the way the absorption worked, would continue. And he tried it for a variety of different with a variety of different parts of the spectrum. And the thing is, he found out that this whole thing, that that black bodies, all bodies, rather than heating to an infinite degree in terms of continuing to absorb heat, reached the maximum and then began to emit heat. In other words, these black bodies, which were supposed to absorb everything, themselves became emitters at a certain temperature, at a certain absorption of energy. They began emitting this again. This was supposed to be also done in ultraviolet as well. Things are supposed to be infinite again, even up to the ultraviolet range. He went and took a look at the ultraviolet range, and again, he found the emitters and not the total absorption. And this actually was, for some reason, was termed the ultraviolet catastrophe. I have to go back and sort of do a better look at the history in terms of why they actually considered this to be the ultraviolet catastrophe, because it really had to do with thermodynamics more than anything else. But it was the ultraviolet catastrophe that sort of set things off, and this is where Einstein picked up the work of Planck, and Einstein moved the ball a little further, and as both Planck and Einstein moved the ball further, what began to happen was all the neat science that you had before in classical science began to unravel. And it was from the work, actually, and I think this is part where the problem was too, is they were able to show that under ultraviolet radiation, certain objects would start giving off electricity. In other words, you would have ultraviolet radiation. Instead of behaving like a wave, it began behaving like a particle. And the thing is that I think this was one of the other things that Planck was looking at, was looking into the whole concept of light as both a wave and a particle. And in the ultraviolet region, you began to see the particle-like nature of light, which was supposed to be simply a wave, and you weren't supposed to see particle-like behavior of it at all. But yet, in the ultraviolet region, that's exactly what you saw. And this is sort of, if you will, this is sort of the precursor to solar arrays. The solar arrays work basically on the principles that Einstein and Planck had been working on. And again, this was something that was not supposed to happen classically. Things were supposed to be well determined. It wasn't supposed to that light was not supposed to behave anything other than a wave. Throughout all the spectrum of the electromagnetic spectrum, light was expected to behave as a wave throughout. But here it is in the ultraviolet spectrum, and it's ultraviolet part of the spectrum, and light is now starting to behave like a particle. So this kind of opened the door, I call it open the door. The classical scientists term this as the ultraviolet catastrophe. This is the thing that began destroying classical physics. It wasn't until you get to the atomic bomb where you had the proof of Einstein's E = mc squared that you really had the end of classical science. That the whole mindset that things were determined, and it's basically the deterministic period of science comes to us in two forms. It comes in the classical form in the early 1800s up until the late 1800s, and then from the late 1800s to the early 1900s, you have modern science. In other words, you have a generation growing up after the classical scientists still heavily believing in the deterministic physics, and they're sort of the next generation, and everyone thinks they're free and clear. Then all of a sudden, here comes the atomic bomb, and people kind of have an idea of what's going on because they hear all this murmuring coming out of the physics community that things are not going the way they should be going, and that this whole concept of a deterministic universe is going to start to fall apart. And that's actually what happens in 1945. The deterministic universe falls apart. Quantum physics begins, and quantum physics, unlike classical physics and modern physics, is fully probabilistic. It's a probabilistic theory. It doesn't put any determination within the universe itself. Further, you have Heisenberg, one of the scientists in there, who is essential to quantum mechanics, basically coming up and stating that there will always be some degree of uncertainty. And the experiments are more specific than this, but for our intents and purposes, we're going to look at the general implications because we're not going to be doing this. We're not covering all of quantum mechanics, all of quantum physics. Here, these are simply the musings, or sort of the rethinking of some of my ad hoc notes, and the research is going to continue forward. And so this is one treatment that's going to come, one treatment of many that's going to come later on. So we will be getting into the more specifics. We will be getting into some of the heavier mathematics, but not right now. Right now we're keeping things rather general and getting a general understanding, a general feel for the science, the understanding behind the mathematics. So and that's why we're talking about Heisenberg. And Heisenberg introduces something known as the uncertainty principle. The uncertainty principle, as you sit down and take a look at it, if you start doing research on the uncertainty principle, and I did a lot of work on the uncertainty principle. A matter of fact, what I've done is taken the uncertainty principle to what's called the nth degree. I've taken it as far as it will go. And for physicists, someone will say, no, you need to take, that's not as far as you can go. You can go nth plus 1. Okay? That's the furthest you can go. And that would be the physics term for it. But we'll just call it the nth degree right now, just for convenience sake. And I did this stating that given a total uncertainty, in other words, given a random walk, and this is the one of the statements in examples in quantum mechanics is the random walk, and the random walk basically says that because the universe is probabilistic, you only have a random walk, and therefore everything remains random. I mean, what happens is that in quantum mechanics, there's nothing really sort of absolute. Everything is, in many cases, random. And this is where a lot of people talk about the random universe or a relativistic universe. And they take this to an extreme degree and say, well, the universe is chaotic. And this is actually where you have the emergence of chaos theory. So those of you who might be interested in chaos theory, this is exactly where chaos theory begins to emerge. So I took that approach. I said, well, okay, let's try the random walk out. Let's see if I can build a research institute entirely on the random walk. And the random walk basically means you have no idea where you're going. There's no expertise in it. You're simply picking a point and starting from there and working your way out. And there's no specific thought into it. You're simply picking a point and working your way out. And that's exactly what I did. I spent about 5 years building a library using the random walk. Went out, looked at old bookstores, looked at, tried to see what I can get for cheap, because I really didn't have a lot of money. No one's going to fund a brand new institute, particularly if they're not part of a major university. And so that meant that I had to go out. I had to find all the different books that I needed to build my basic library, and I had to find it at a very cheap price. And so the best places to go were either to close out sales, these warehouses that had all these books for sale, because the bookstores were overstocked, and they sort of dumped a lot of these books into these warehouses. And you go into a warehouse, and there's these shelves, or warehouse shelves, and they're filled with books. They're full of boxes of books, and you walk through the warehouse, go through the boxes, and you randomly pick up books, and you'll find books for $2, $3, stuff like that, and you can pick up a whole bunch of good books. Like that. And more often than not, they'll have old books in there. They'll have out-of-print books in there. So that led me into, say, let me see what I can find at old bookstores, used bookstores. And I went to used bookstores as well, eventually, and found a lot of good used books from there, and a lot of rare books, actually, that went all the way back into the 1900s, early 1900s. This gives me a good background in terms of what I was reading, of what was going on in science at the time. I mean, there's nothing better in terms of understanding where to go in science than to look back into history. Use history to tell you where you might want to go later on. And so that's what I started doing. The only option I had was to go back, to look at history, to look at the old stuff. And so I sat down and I started reading through this. I started reading through these old science books, and they were quite interesting. And the thing is I did have some newer textbooks. I did have at the time what they call modern textbooks. This was between November of 1989 to about 1995. That's when I built my library. The internet really hadn't come up yet. There were servers you could log into from something called INET 2000, but the articles that you got, the time you spent on them was very expensive, and so I really didn't do that too much. So that's it. That I spent most of my time wandering around Toronto looking for different book warehouses and warehouse sales and old bookstores. And it was an interesting time because my job at the time entailed wandering around looking for books and then eventually reading books. That was what I did for a job, and then every once in a while, if I can get a consulting contract for helping people out with IT and doing computer science work, that's sort of what paid the bills. And that's how my institute began. But again, all based on the random walk, based on testing out the ideas that the universe is rather well random and no order comes out of it. And so as I began doing that, I realized that that's not necessarily true. That you can use the random walk to go out and do things. But as you do the random walk, you collect whatever you're going to collect out there, and you bring it back, you put it into a pile, then you go out, you collect again. And as your pile starts to grow, you start to organize it. And initially, by appearance alone, you try to sort and organize your whatever collection you have. And this is what I talk about a library. A library is nothing more than a collection of things and objects, because that object can be people, that can be information, it can be books, it can be objects that tell you something about a place, it could be rocks, it could be, anything that you collect and then eventually organize. That's a library. And of course now that means you can have a variety of different types of libraries. You can have an audio library, you can have a video library. Inside of an audio library, you can have a library of sounds, you can have a library of music, you can have a library of various different types of music. It really depends on how you collect and how you organize. That really sort of determines what's going to be in your library. And the thing is, this is how, and again, you're testing out the random walk. Random walk is you go out, pick a point, start from there, and let your interest sort of guide you where you want to go. There's no particular rhyme and reason to it. The old scientific method, the classical scientific method of hypothesis, method, observation, and conclusion are completely, that's gone. What you do is you strip off, and this is sort of called open exploration. Open exploration takes the random walk. Because you're doing a random walk, you're not actually fitting your exploration to a particular theory. You're allowing the information that comes in, the information that you experience during the random walk, during your experimentation, to dictate how the theory is then going to form. In other words, the theory forms out of the information that you collect, that you in sort of basically the observations that you make. So basically all you have is you have method in the open exploration method. You only have method and observation. Both hypothesis and conclusion are gone. And it's simply because you're not dealing with, and I got to make sure something's, you're not dealing with, okay. I just had to check my microphone for a second there. You're not dealing with trying to prove something. So all you need is you need only the method and observation. And your method is rather simple. Go out, pick a point, and it's a random point, doesn't have to be anything specific. Start collecting, go back, organize it, and then if you think you have enough to organize, you do the organization. But if you don't have enough to organize, you simply go back out again, and you keep collecting until you do have enough to organize. That's your method. That's the entire method. So what you're not doing is you're not going in with a preconceived idea. You're not going in with any form of prejudice, because you have no idea what you're going to find there, and you have no intention of going in to find something. That's the thing. Is this is what's good about a random walk is, in terms of being objective, is if you have a hypothesis, a thing you want to try to prove. Right, try to prove your own theory inside of an experiment. You now have a bias. You have a prejudice in there, and that's going to influence the way you set up your experiment. But if you're used to the random walk, if you're used to open exploration, then there is no bias in there. It's simply the experimentation itself and the experience from the experimentation, or exploration, I should say, because experimentation does exist within exploration. It's a type of exploration, if you will. And that provides you with your understanding of what you're seeing. And I think it doesn't provide you with a complete understanding. It provides you with a partial understanding. And so as I said, I built my library for 5 years. It took me 5 years to build my library, sort of the base library. And then once I built my base library, then in 1995, I began my first research desk, and the first research desk was simply to go out and see whether or not I could start adding more to the library, looking at different things. And again, there was no specific direction. There was no particular idea of where things were going. But I began to understand, as I began reading through the scientific literature, through the scientific history, that what I had been taught in textbooks, what I had been taught in school about the deterministic nature of science, that this was not the case, that science was very much uncertain, that there was a lot of unknowns, and that every time you actually produced an experiment, it produced more questions than it did than actually provided answers for. And I began to sort of see this. I began to sort of okay, this is the way researchers see things. I began to see that the researcher view of science was completely different than what was actually being taught in school, and the rigidity that you would have in science melted away. And this is sort of when I began to realize that there was something more going on, particularly in quantum mechanics, than had sort of met the eye. But I didn't know what it was. I really didn't have a definition for it. But so it took me a couple of years beyond the 5 years of building the library to sort of test out this random walk and see, okay, I was building something from the random walk. I could see I was building something from the random walk, but what implications did this have in physics? And then the next question, when I saw the implications, I needed to ask myself and sort of see and go find evidence. Did other scientists see the same thing? In other words, independent of my own research, did other scientists, other physicists see the exact same thing? Did their results produce this sort of, yes, you go in random, but at the same time, there is a degree of order. In other words, you're looking for not total order, not a total answer, not a total or an absolute knowledge, but looking for an answer in, this is the calculus term, in the limit. And this is where I began to realize, and it took me another 5 years to realize that the random walk and the Heisenberg uncertainty was really revealing something new about the nature of quantum mechanics and the quantum physics universe. And that's that we're dealing with knowledge as an asymptotic curve. That you can only approach knowledge, you can never absolutely reach it. And this meant you're dealing with a limit, and you're not dealing with call a certain or deterministic line. It's not a straightforward line. The graphics and curves are not straightforward. You're dealing with something rather complex, and that the best you can do is approach the knowledge within a certain degree. And once your knowledge is complete within that certain degree, and you can try to push it forward further, but you're still going to have that uncertainty. No matter how far you push this knowledge, the uncertainty is going to continue. And ironically enough, this is some of the conclusion that I was watching just a couple of days ago, but actually about a week ago. I watched one of the researchers working on CERN. He was working on the Higgs boson particle. He was presenting his research on the Higgs boson. And particularly, he was comparing the Higgs boson, looking at the Higgs boson within the concept of quantum field theory. This is sort of the quantum mechanics is a whole variety of things. Quantum mechanics emerges as a theory. Then, as people research on it, because it's not a fixed and final theory, as people work on it, it changes, it evolves. It will break off into distinct branches. In 1985, when superstring theory came out, it came out as an initial theory, and within a year, it had broken up into 5 or 7 different distinct theories. And today, you have basically 2 theories left, and that's primary. And the one that's most favored is the M theory, which gives us 11 dimensions in the universe. It gives us parallel universes that are right next to us. It could be literally right on top of us, but we just don't see them. It gives us dark matter and dark energy. It gives us wormholes. And the thing is, as they measure as they try to sort of use the telescope and with the Hubble Space Telescope to try to measure the mass of the universe to see how much is there, and put this back into your equations again, the things you think you understand, your quantum mechanics equations. and your general relativity equations, all of a sudden things stop working. You have to add in this mass that you don't see, and what that mass you don't see that's not seen is both the dark energy and dark matter. And the question was, well, how much dark energy and dark matter do we need to get our equations working properly? And the answer was 95%. And this, people hear about dark energy and dark matter, but don't understand the consequences of it. The consequences of it, and this is where the research comes in. This is where, if you're a researcher, this is what you're interested in, is that the dark matter and dark energy define regions within your equations that don't match what you see in the telescope. In other words, they don't match your experimental results. So in order to get your equations to meet these results, you create these imaginary masses and imaginary energies. This is the dark matter and dark energy. And in these equations, in order to get what they were seeing through the Hubble Space Telescope, they needed to make this imaginary energy and mass 95%. 95% of the equation was this dark energy, dark matter. Only 5% of was what we saw, and so this causes a huge problem. It says right now the closest certainty that we can get to anything in the universe is 5%. I mean, that's not at all confident. That's not confident. That's lack of knowledge, if you will. And it just serves to sort of point out to say that, as you're doing this exploration, the reason why you're going into this exploration because you're the type of person who enjoys going into the unknown, going into the unexpected, and trying to figure out what's what. If you don't enjoy this type of stuff, you don't enjoy that level of risk, then don't become a researcher. That's the basic gist of this thing. There is no expertise. There's no guru. There's not even need for the Nobel Prize. The Nobel Prize, in many ways, is meaningless because you're not an expert. There's still so much more to learn. You go into this simply because you have this sort of question in the back of your mind of, well, how does the universe work? And that's kind of where I am at. I'm now 25 years into this. At 5 years on the research desk, 5 years building the library, 20 years on the research desk. So I'm 25 years into this. And I'm just now getting to the mathematics because when I realized that the universe was starting to fall apart and that the universe was anti-logical, you couldn't actually match up a logical mathematics with an anti-logical universe. This is one of the reasons why you had all the fudging you had, the way you had to fudge your equations in order to meet your, adding in the imaginary dark matter and dark energy into your equations because what you actually understood was so poor, and you're trying to use a deterministic mathematics, a logical mathematics, to describe an anti-logical universe, a universe that is under no obligation to follow our particular sense of logic. And again, it's not that the universe is anti-logical; it's anti-logical from our perspective. The logic we describe as logic is our own logic. And there is no reason why that the universe is bound by any rule or reason to follow what we say has to be true. We are not, and this is what this shows us, is we are not in control of the universe. Our minds cannot control the universe. Our minds cannot encompass the universe. We can understand it to a certain degree, but we don't have the absolute knowledge. And this brings us back down to the question here. And then you say, well, what do you see this instead of seeing this in astronomy and physics? Because you see this in black holes. Black holes are described not by what we see, but what we don't see. Black holes are never seen. The reason why we know a black hole is there, or we think we know a black hole is there, and this is the better term, we think we know a black hole is there. It has to do with the fact that we see the effect on the surrounding environment. When we see the effect that we expect to see around a black hole out in the stars, and this has happened, and they've found candidates for black holes, and they've been studying, and the theory around black holes has been changing. Why? Because as they found more candidates for black holes, they began seeing different characteristics. They began seeing different behaviors, different physical properties, and a variety of different things that sort of allowed the theory, and this is the way it should be done. The theory adjusts to your experimentation. So your theory takes a backseat and is led by experimentation. It's led by experience. That's the way things should be. And then this, as a physicist, this is my basic understanding of science: that it's experimentation, it's observation that leads, and that theory falls behind. When they went in to sort of start testing this on a micro level, on a level on quantum mechanics, they began trying to box in electrons and look at electron pairs for quantum computing. As they began trying to do this, they thought they had trapped an electron inside of a box, and all of a sudden things began on their monitors began appearing outside the box. And this was at the same time they went back to their monitor and see, did you have this electron trapped in here? And they did have the electron trapped in here, but you had the sensor going off over a variety of different places, and they realized that this electron pairing thing, this whole thing of trying to change the electron spin up or down, were causing problems all over the place. The experiment that they thought they had boxed in was not in the box. It had gone outside the box, simultaneous to the events that were going on inside the box. This wasn't after or before. This was at the same time the events were going on in the box. Inside your electron box, you had events going on with electrons outside the electron box. So this began to sort of unnerve people and unnerve physicists to say that there is a lot more here that we don't understand. Some of them have actually started to come up with theories that our universe is imaginary, and that our perception, how we see the universe, changes how we see what's going on in the experimentation. So there's a number of things like that. There's a number of uncertainties. And so you do have independent confirmation that, well, you do have some degree of understanding. There are things, again, that you don't understand. And this is sort of how science is done. This is how research is done. And this sort of leads to a conclusion of mine that well, while you do have the random walk on, and the random walk does work, it's only to a certain degree, because you do have knowledge. It's just you don't have absolute knowledge. You have a certain degree of knowledge. You have a certain degree of understanding, and that's as far as it goes. So where does this leave us now? Because we're talking about is atheism dead? And I said the reason why I'm bringing this up is we're not answering atheism from the religious perspective. We're going into the physics, because atheism was built on physics, and therefore, as physics changes, as physics evolves, we need to understand the implications on atheism for this. And there certainly is implications. Atheism was built on the deterministic physics, on deterministic science, that science was absolutely understood, that the world was absolutely understood, and the world worked in law and order. This is not the case now. The case now is that we are in a probabilistic universe. We have the probabilities of parallel universes. We have up to a possible of 11 dimensions now. This is the consensus, and this leaves the door open for a spiritual universe that's parallel to our own. It leaves open the door for the possibility of God, and it certainly, at a very minimal level, states that gives you a sort of a position that you cannot state with any degree of certainty that God is dead, or that there is no God. I mean, the initial comment, and this is why I've phrase of given the title of this talk the way I've done this. I said atheism dead, because this is the question that was posed later. Is God dead? The beginning of the atheistic period is God dead? And the question was, because we had deterministic science and they thought they knew everything, they knew that they had the absolutes. The answer was yes, and so that's the beginning of atheism. So if your beginning of atheism is on the certainty that God does not exist, that man's mind is superior to all, as quantum physics comes up and changes this, and this sort of reality, we're past actually. We're still within. Well, we're certain to a certain degree. We're within quantum mechanics, but at the same time, we're now moving toward. We're moving into and bringing superstring theory along as well. And then the superstring theory brings up the same problems and consequences. There's no real conflict between superstring theory and quantum mechanics to a certain degree. And I'm not going to say it absolutely, but to a certain degree, there's no conflict with them. You can work with both theories, and so you can say that to this point, you cannot state that there is no God, because the deterministic universe that the atheism was built under is no longer exists. We're now in a probabilistic universe. So you can only state within a very loose degree of probability that God is dead. The fact that you now have parallel universes, which opens the door for spiritual universes, further moves a notch to say, well, given that you actually have ancient documents describing heaven as a parallel universe, as a separate universe from the physical universe, well, this is exactly what well, one can not going to say exact this because this is a wrong term to use. This is what you can find in a comparison to a parallel universe. This is a fitting description for a parallel universe. And in many ways, if you go back into the ancient literature, this is the Greek literature, this is the in some cases the Hebrew literature, into the Hindu Vedas, you'll find these descriptions of parallel universes. So this opens the door again, seriously opens the door again to these spiritual universes, and pushes the needle further into the armor of atheism, if you will. And we are now injecting the poison that will eventually kill atheism, because the science itself does not support atheism anymore. The very scientific base that atheism was built on no longer exists. And as this continues forward, this is going to pose a problem. Well, not necessarily going to pose a problem for atheism, because atheists, well, all they have to do is turn a blind eye to this and pretend that none of this, that quantum physics, that superstring theory, and everything else just simply doesn't exist. And a number of scientists have done that. The number of scientists who are actually going into quantum mechanics and into superstring theory are very few. And even when some of them do go in there, they stick to their own views. And they say, well, superstring theory is simply just a theory. And that's as far as it goes for them. And so they can live happily with their own beliefs in whether they believe in a God or not. And I said both sides will do this. Both the theist side and the atheist side will stick to their beliefs no matter what evidence comes out of science. But if you're an open researcher, you do have to take a serious look at this and not to particularly stick your own view in it. But the thing is that, what am I finding? I'm finding that you know, parallel universes are a fitting description for for heaven, as a spiritual universe. So a spiritual universe described as parallel to our own. Well, this is exactly what we this is exactly what we've seen in M theory, in the sort of the parallel universes, the 11 dimensions. Well, you know, then yeah, this is this, and it fits exactly. But the thing is, it's exactly so it allows you to say now you have a good probability saying that, you know what, we need to go back and take a look at theology not as a religion but as a science. View it as a metaphysics, if you will, metaphysics, and then treat metaphysics in the exact same manner that you would treat either quantum mechanics or superstring theory. Look at things in terms of probability, and then if you want to go further than that, what you do is you go into religious texts and take a look at what religious texts actually talk about probability as opposed to being deterministic. In other words, if a religious text talks about absolute certainty and fate, or gives you something that's deterministic, and you understand the universe to be probabilistic, you can say that at least the understanding of the mechanisms of the universe is not within this within this document, or religion as it's defined, or theology as it's defined, and now you're only looking for elements of similarity, or elements that sort of would give you some idea of what these people thought of the spiritual universe. And it's not until you do find, and if you find a theory, a theology of metaphysics that is probabilistic, and again, it doesn't. This is where it comes in again. It doesn't have to be absolutely probabilistic. It can be partially probabilistic. It can be partially probabilistic, and have some degree of what we'll call determinism in there. But even in some cases, if you look at I can know from what I've been researching, the different theologies I've been researching, I've found one, and I will be presenting this later on, though, that does give you a rather probabilistic view of God, and it is itself rather probabilistic, but it does present determinism and deterministic views. But the deterministic views are only conditional. There's within certain conditions, within certain bounds themselves. And then outside that, you have a lot of room for more probability, a more probabilistic spiritual universe. So again, and what you do see is a universe in terms of this description that is asymptotic. There's no absolute we can't achieve absolute knowledge, that we can only approach it. Again, you're seeing this asymptotic curve for knowledge, and this is exactly what I saw, what I've been seeing in quantum mechanics. This is what you see in superstring theory. This is what I see in the research for the Higgs boson, the different researchers who are working on the data, who are working on the matching it up with the different theories, that you have something that is probabilistic and not deterministic, that there is a certain degree of uncertainty, and you're seeing this sort of repeated pattern. So yeah, it is in its own ways very interesting. It's sort of definitely an interesting way of understanding how the universe is put together. But at the same time, it gives you, I don't know how many people will sort of stick around for the heavy mathematics of this. I mean, people will argue atheism back and forth, but they'll argue on the spiritual grounds they know, and they'll primarily stick within the limits of their own knowledge, the limits of their own understandings of things. They won't really push their boundaries too much. So they never really challenge what they know. And it's not until you actually do that you begin to see that, well, maybe there's room for other understanding. And I think this is once again where we're talking about sides of an argument. Two people are arguing over something in terms of what they've seen. And if you see something, you see an object. Let's bring this up here. With up that I have in front of me, I have a wrench. Okay. Now, you see this side. I see this side. And in our descriptions, it may be to such a degree that the only thing we can see is our own sides. So if I begin arguing with you about my side, and you begin arguing with me about your side, we both will be right. We both have a degree. We both could be right about what we see, because we're describing two sides of the exact same thing. I'm talking about and arguing about my side, and you are talking about and arguing about your side. At the same time, and this is sort of one of the conditions that you have, even in mathematics and computer science, this is the one condition that you have. You also have a not condition. And a not condition is where, rather than both sides being correct, right, you have both sides being wrong. In other words, I'm arguing my position on something. You're arguing your position on something. But because of the things we haven't seen, we're leaving out the argument themselves because it's beyond our experience. We leave things out. Both arguments, both sides of the arguments are wrong. So this is one of the things that happens, and is one of the consequences of a probabilistic universe, is that things may not appear as they are, and that you do have to go take a second look at them. You shouldn't be going in with a determined point of view. My best point of view, in terms of, in my opinion, in terms of what I've experienced, the best way to do research is through open exploration. Use the method of open exploration, and it's basically method and observation. Get rid of hypothesis, get rid of conclusions, and all you have left there are method and observation. And this will go a long way. But from my experience, from the different experimentations that I've had in open exploration, what I'm going to be presenting is that atheism is dead. That the initial grounds for atheism are gone. Atheism does not survive in modern physics. I'm not going to use modern science because modern physics and modern science are actually two different things. I will get into the differences between physics and science, particularly modern physics and modern science, and what we term modern physics and modern science. Not that as physicists, understanding that physics is the pinnacle of science. So if atheism doesn't fit within physics anymore, because the fundamentals have changed, then what's going to end up happening is that the only conclusion that you can draw, again from observation, is that atheism is dead. That doesn't necessarily mean that it's dead in people's minds. People are going to still going to be atheists. It just simply means that the initial argument stating that atheism isn't a religion because it's scientific fact is no longer the case. So atheism moves back down the ranks from being scientific truth to being a religion. It's a belief. And I know a lot of atheists are not going to be happy with this, but this is what the science is. This is what the science is. This is what and I'm using science as being synonymous with the term physics. So physics says that you can't give the term atheism any absolute meaning, and a lot of other evidence that I'll present later on will show that atheism doesn't have really much scientific evidence to go on. So it's more of a belief than anything else. So that brings you back down to a religion, and as a religion, you can believe in anything you want to because it's about belief and faith as opposed to any degree of reality. So that's about it. It's about 10:57. I now have to move on to you now. If you follow me on Twitter, you will see a lot of the stuff broadcast. You'll see the various links being broadcast, so you can sort of follow me along on there. I don't mind if you ask questions. I had the chat up. I had one person watching, but I don't know how long they stayed watching for. They stayed pretty much a good time, but they didn't post any questions. They didn't say hello or anything like that. But the thing is, I'm happy I had one viewer. That's a good thing. So if you follow my Twitter, and my Twitter is posted on my account, the link to my Twitter account is there. Follow me on Twitter. You'll find out when these broadcasts pop up. Come by, talk, listen. If you don't agree, post whatever you want. I'm not of any opinion. If you watch this later on, let's say you're watching this later on, and you have a comment, leave a comment. Good or bad, doesn't bother me. Anyways, that's it for now. I'll see you on now in about 5 minutes. I'm moving over there just now. I just got to do some cleaning up, to take down the lights from this broadcast. Move over to the section that I have, the device on, and go live. All right, take it easy. Bye-bye.